All right. So good afternoon. So first, let me thank the organizer for giving me the opportunity to present today one part of my research activity. Just a warning, don't try to find too much of a continuation with the previous talk, and don't blame the organizer for that. I've just been called in last minute to swap with another speaker that couldn't make it. So we're just going to try to end up the day smoothly with some gas phase spectroscopy and chemistry. So yeah, photo processing of positively charged nitrogen bearing, and more specifically N-heterocycle and cyano-PAH. So let's start with a bit of context. And so here it's in the context of this hunt for the origin of life and this nitrogen containing cyclic aromatic molecule, which are supposed to be building block for such as nucleobases. And so those images are actually taken from a review from Sanford and co-workers. I apologize, Jean-Claude. I think there they call it prebiotic chemistry, but I'm sure it's meant in terms of origin of life. So N-heterocycles have been found in Titan atmosphere. They have been found in various meteorites, but their extraterrestrial chemical formation remains elusive, and it still remains undetected in the interstellar media. So recently there were a paper published by the Gotham team where they unsuccessfully searched for these N-heterocycles toward TMC1. So maybe Chirote has something in the bag, and soon we'll get a crack at it. But at the moment, they remain undetected in space. Oh, I mean, in interstellar medium. So the other bunch of molecules I want to talk about today are those aromatic nitrile species. They have been detected in TMC1, and for the case of benzonitrile, they have been detected also in pre-stellar and protostellar sources. But if you look, for instance, at the last, I think, or one of the last modeling, trying to compare the abundance of benzonitrile derived from the observation compared to astrochemical model, there's still few order of magnitude off. And so there's clearly here a lack of the understanding of the chemical composition or network and reaction network that can produce those cyano-bearing species. And so, I mean, I've been saying that I would be looking at charged nitrogen containing species. And if I take the example of here, benzonitrile. So for the protonated one, you can have this proton transfer from H3 plus or from HCO plus. I'm not sure. I don't know if I heard what is proton affinity of benzonitrile and where it lies on this nice curve we got yesterday from Marcel. And for benzonitrile radical cations, in this you can get in peer or edge of dark clouds, where you have photon flux up to 13.6 eV, and the IP of benzonitrile is below 10 eV. And also, I mean, I'm not a specialist, but it seems that you can also get some UV radiation inside dense cloud from this H2 emission after impact from electron resulting from cosmic rays. So the motivation here were on the investigation, the effect of this protonation on the VUV photostability. So basically, does adding this proton, like protonated species, will help it to survive to the harsh environments in space compared to its causing the radical cations, and trying to rationalize a little bit the undetection of N-heterocycles. What is also the potential role of this protonated cyanoaromatics as a neutral counterpart have been detected ubiquitously now in space. And I mean, the most of the ions detected so far, at least in dense molecular cloud, are protonated species, and evaluating also the importance of top-down mechanisms, even for small species. Okay, here small for me means a few rings. But, and the method for doing that is to use this SRMS2 machine, which is basically combining an ion trap, a commercial ion trap, with a tunable UV radiation. So this happens in Soleil. So it's a commercial LTQ, so it's a quadruple ion trap where you can just inject the UV radiation inside. This happens on synchrotron Soleil, on the Désir beamline. And so this is work done with Laurent Nau and Alexandre Giuliani. And in this, I also have been collaborating with some people I met back in the day when I was postdocing in Melbourne. So with Adam Trevitt from University of Wollongong and Chris Hansen from University of New South Wales, Sydney. And so the idea is you can inject ion that you generate them either with electrospray or atmospheric photoionization or chemical ionization. You must select them in the trap, and then you can irradiate them with the VUV and detect the different photo fragments, ionic photo fragments. So I start with the most simple one, the protonated benzonitrile case. Some of you might have seen the preliminary result on that, 2021 at the GSM in Rennes. And this actually led into a collaboration with Jennifer Noble. So she was also attending and said, oh, we also measure part of this. And so maybe we should do something together. And so here you can see the results at the PIM. So using the cryo ion trap where they measure transition to the S1 and S0 state. And here are the results from Soleil. So here it's a total photo product yield. So you basically take all the photo fragmentation channel, you sum them up, and you plot them as a function of the photon energy excitations. Here's a DFT simulation that produces fairly well the spectrum. And here you can see a breakdown of the different channels. And what is interesting is, so the main channel is basically the loss of HCN or HNC, leading to the phenolium. But at low photon energy, you can see that this phenolium, so MZ77, react really strongly with residual water that is in the trap to form this MZ95, which correspond to the protonated, probably to the protonated phenol cations. And so what is interesting here is that you can clearly see a change of reactivity in the formation rates of, so comparing the formation of 77 compared to 95. So one way of seeing it maybe more clearly is just to plot them. And so you can see here 75 in blue and 95 in black. And what is funny is actually like a resonance shaped thing. So you really have this change of reactivity peaking where the transition toward this S12, here, state thing is. And I mean, if you try to guess a little bit what's happening here, the only thing that you can see is if you look at the other main transition to this S2, for instance, or this S8, you can see that those are typical pi-pi star transition, whereas the transition to the S12 states completely disrupt this pi symmetry. And so you can potentially speculate on disrupting this pi aromaticity can lead to an isomer, a C6H5 plus isomer that with some ring opening mechanisms. And so the idea, and so what is interesting is this C6H5 plus is known to be a key species in the formation routes of aromatics. So in case of benzene, where you get this radiative association with H2 followed by dissociative recombination to form the neutral benzene. And you also had some ion neutral reactions, experimental things that show that you can really build up with this bottom-up approach a lot of different PAH. And so here the idea is it might seem like if we get protonated benzonitrile in space, it might be important in the process of PAH growth, but in an indirect fashion, as it will be a two-step process because you first need to photofragment this protonated benzonitrile before having the chemistry happening. So it will be rather slow mechanisms if this does play a role. And just quickly, because I said I will talk about charge. And so, I mean, the protonated benzonitrile work has been published, and in there you will find no spectrum whatsoever of the radical cations. And the main reason is, so here you have the result, and the main reason is we lose CN, as in the literature you can find a lot of different work on the photodissociation action spectrum of this animal, and you always will find a loss of HCN. So we never really understood what we were observing. If we were forming another isomer, we tried to simulate using quantum chemical calculation, and we never really fully understood what it was. So we just left it apart, but we still measure the larger PAH. And here, I mean, you can see the two isomers of the cyano-naphthalene that has been detected. Here you can see the anthracene and phenanthrene. And so in all the cases, what you can see is, surprisingly, you have a lot of structure in the spectra. And the photo fragment is always super reactive. So this loss of HCN, which forms basically a mono dehydrogenated cation, seems to be highly reactive, at least toward waters. And in this case, we also, of course, plotted the different, the relative, basically, branching ratio. And what is funny is you can see here we don't have this resonance phenomenon, but we do have some crossover for the cyano-naphthalene, and we have a push. I mean, they're pushing over, and it's always the not always. Here you can see the 195 going like lower, and this we tentatively rationalize it, because when you start with phenylium, the most stable form is actually singlet. When you go to naphthalene, the singlet and triplet are nearly isoenergetic, and when you go larger, as you go larger and larger, the triplet becomes the most favorable one. And actually, the triplet one is the unreactive one with water. And so that might be a way of explaining this, but this is still work in progress. Adam Trevitt is taking actually some kinetic spectra in his lab with the same LTQ that is in Soleil. And here a little teaser on future experiment on series. So this would be with Christian Alcaraz, Claire Romanzin, and Roland Thyssen, where we actually just looked quickly at forming C6H5+, so not the very most efficient way, starting from naphthalene in this case, and we actually saw a big change in reactivity as a function of the photon energy, so meaning as a function of the internal energy of the ions. So we also recorded the radical cations, and I mean, I'm not going into detail because we haven't looked at it so much after what we saw. We were unsure how much we can trust the radical cations. As to form them, it's a really harsh way of producing them. So, I mean, we'll get back at it, but first we wanted to figure out all this chemistry, this singlet triplet chemistry that is probably happening. And I talk about N-heterocycles, and I talk about the effect of protonation versus radical cations. And here in this case, we never managed to form the radical cations. No matter what we did, even using the photoionization source, we always form only the protonated. And here, basically what you can see is you always get the H2 loss and the HCN or HNC loss with different branching ratio, but those are the two major channels in this case. And then it seems that they're actually quite similar in this case. But here, what is funny, it's again, in the case of quinoline and isoquinoline, we again form this intriguing phenylium cations, which again shows a strong reactivity toward waters. And so just to conclude on those N-heterocycles, then as I said, so the four system exhibits a similar dissociation channel associated with H2 and HCN loss, but with different branching ratio. What is interesting, it seems that increasing the size of the N-heterocycle increase the chance of retaining the N atom in the larger ionic photofragments. That protonated N-heterocycle in interstellar space are unlikely to be precursor of larger N-containing species because, I mean, as you would try to build them up, they will break before you manage to make them big. And that protonated pyridine, quinidine, isoquinidine, and acridine, the four we measure, are most likely to retain their nitrogen atoms within planetary atmosphere where you are shielded from the UV radiation, so suggesting that such environment are more likely good substrate for prebiotic chemistry. And with that, I would like to thank you for your attention.